Today we are going to be talking about quantum numbers and electron spin. But before we jump into these, we are going to talk briefly about what quantization means. Because if you're anything like me, when I hear the word quantization, I don't know what people are talking about. So quantization is the concept that a physical quantity can have only certain discrete values. Things like the electrical charge, energy, light, angular momentum, and matter are all quantized on the microscopic level. Also, the energy levels of electrons and atoms are quantized. So basically, in summary, this means that things can only have certain discrete values. We can't have a value like pi because it has so many decimal points. It needs to be an integer value. So this guy, Niels Bohr, he is a Danish physicist that made fundamental contributions to understanding atomic structure and quantum theory. He received a Nobel Prize in Physics in 1922. He assumed that the angular momentum of the electron must be quantized, resulting in discrete orbitals and energy levels. So this is an example of the Bohr model. This is a hydrogen atom that he studied, and he theorized that the electron has to have a certain discrete orbital to be able to go around the nucleus. Now, to think a little bit more about quantization and electrons, we're going to think about electrons as waves. Electron orbitals are created when the wavelength fits along an orbit. Because of this, it will only be an integer number of wavelengths. So this means if we have our atom on the left here, in the center, we can see our nucleus, and surrounded by it is our orbital with our electron moving in a wave-like pattern around the nucleus. We can see that this has constructive interference, so the wave is going to continue around. Now, the one on the left, we can see that our wave that our electron is traveling along has destructive interference because it does not have an integer number of wavelengths. So on the right here, this is an example of the different electron orbitals, and you can see the different wavelengths that go along each one of these orbitals. And as our electron travels along these wavelengths, we can see that there's only a certain integer number that we can have. Now we're going to jump into our quantum numbers. Our quantum numbers define where our electrons likely are in space. And this is an important concept to understand. When we talk about our quantum numbers, we're trying to pinpoint where our electrons are, but we can only understand the likelihood of where they could be. So first, our first quantum number is our principal quantum number. It is shown by our symbol n, and it describes the orbital size and our energy level. So our allowed values for this is 1, 2, 3, etc. So we have our orbitals here with our integer numbers, and we can see as we go farther and farther out from the nucleus, our principal quantum number n is going to get larger and larger. As we go out and increase the orbital size, the energy level of our electrons also increases. Now, going over to the periodic table of the elements, we can find where our first quantum number is using this periodic table. So on this column on the left, we can see numbers ranging from 1 to 7 along the sides of our periodic table, and these are our orbital numbers. So if we have n equals 1, we know that our element is going to be either hydrogen or helium because it is in the first row of the periodic table. Moving on to our next quantum number. Our next quantum number describes the angular momentum of the electrons and its orbital shape. This is symbolized by the letter L. The allowed values for this is 0, 1, 2, etc., etc., to n-1. And if you are familiar with chemistry, you might have heard of the sp, d, and f orbitals. Now I'm going to draw what these orbitals look like. So first off, our s suborbital over on the left here looks just like a sphere. So imagine this in 3D space. This is going to be a perfect sphere around our axes here. Then if we move over to our P suborbital looks kind of like two teardrops that are put together. Some people also call them dumbbells. So you can see it goes along kind of in an infinity pattern, but imagine them as two teardrops in 3D space. Going over to our suborbital D, most of the D suborbitals look something like four of these teardrops put together, kind of in a four-leaf clover pattern, just like that. And so we can see with our orbital shapes that we have certain integers that go along with them. So for our S suborbital, we have an allowed value of 0. With our P suborbital, our allowed value is 1. With our D suborbital, our allowed value is 2. And then our F suborbitals are a little bit weird. We see them as something that looks kind of like that. They just look a little weird, really hard to draw. Lots of stuff going on with our F suborbitals. All right. Now going back to our periodic table of the elements, we can see that our periodic table comes in handy again when trying to understand which suborbital our electrons are going to be in. So these are color-coded. The green shows our S suborbital on the left. The orangish reddish color is our P suborbital. Our D suborbital is shown by the yellow, and our F suborbital is shown by our purple. Our next quantum number describes the magnetic quantum number, describes the orbital orientation of our electrons, and is symbolized by M sub L. Our allowed values for this one is negative L, ranging all the way up to -1, 0, 1, and then all the way up to positive L. So if we had our P suborbital, there are 3 ways we can orient this orbital in space. So if we could have it going along our z-axis here, and we're going to draw our dumbbells / teardrops going along the z-axis. We could also have them going up along our y-axis, just like that, or we can have them going across our x-axis. Now you'll see that all of these look the same, but they're oriented differently in space, which is really important so we can tell where our electrons are going to be. Okay, our last quantum number is M sub s. This describes our electron intrinsic spin. Now the word intrinsic is very important here. There's been a lot of studies talking about the electron spin, and a lot of people have thought that it is talking about the angular momentum of the electron. However, the electrons are very, very small. And so people argue that it cannot have a spin because the electron is so small. And so we describe it as an electron intrinsic spin. That's as if the electron is actually in its axis rotating around itself. So the allowed values for the electron's intrinsic spin is -1/2 and +1/2. The cool thing about this quantum number, it is independent of all the other quantum numbers. Now we're going to talk really briefly about an experiment so we can know the history behind the electron intrinsic spin. This experiment was done by Stern and Gerlach in 1922. They had a electron shoot out of this place here, and they shot it through a magnetic field. Now, as the electron went through, they theorized that it would hit their receiver on the end here, just going straight through. But as they sent the electrons through, they noticed that some would go up and some would go down. And because of this, They described this as an electron intrinsic spin because some were positive 1/2 and some were negative 1/2. They would go up or down depending on how they hit the magnetic field and went through. Now I'm going to walk you through an example of how to find these quantum numbers if you are given a specific element. Now for part of this, we're going to be using our periodic table again. And in this example, I'm going to be using carbon. Now carbon is located right here on the periodic table. So first, for our quantum number n, we are going to be looking here on the rows. So we can see that carbon is located on row 2. So we know that our n is going to equal 2. For our L, we are going to look at where carbon is placed on the periodic table. So we talked about before that our L describes our suborbital shape. We know that that carbon is in the p suborbital because of where it's located. So we are going to put our L quantum number as +1. Our m sub L can have 3 different values that could be correct. Now we learned that our m sub L is either negative L, 0, or positive L, or anything in between that. So we know that for this, we can either have a -1, a 0, or a +1. And then for our m sub s, this again is not dependent on any of the other quantum numbers. So we know that our electrons are either going to have a +1/2 for its intrinsic spin, or it's going to have a value of -1/2 for the intrinsic spin. Hopefully that makes a little bit more sense on how to use our periodic table to find our quantum numbers for a specific element. Okay, so that sums up our quantum numbers and our electron spin. Here's a brief summary of how to find all of our values and what our quantum numbers are. Thank you for watching and have a great day.